So far, everything we've spoken about in quantum mechanics has been about a single particle. We've been imagining the presence of a single particle in a box, and we've been trying to describe the behaviors and properties of just the spin of that one single particle. Today we're going to take a really big step forwards because now we're going to put a second particle in the box. Now we're going to talk about the quantum spin of multiple particles simultaneously. So instead of having a single particle like an electron, now we're going to imagine we have two particles. And once again, we want to describe the spin of the state of the two particles. Now you might think, what's there to know? What's there to do? We already know how it works for one particle, so we just do it twice if we have two particles. And it turns out that it's actually more complicated than that. The presence of more than one particle actually fundamentally alters the behavior of spin in ways that we'll see in a bit. First, though, we need to set down some ground rules. So rule number one, we are only talking about spin here. Particles have other properties besides spin, and so far we've only been writing down wave functions or state vectors describing their spin. And so we're going to continue with that. We are only talking about the spin of these particles. So we are not encoding any information about where the particle is or how fast it's moving or any other information that we might have to convey about the particle. We are just talking about spin. And in particular, we're continuing to confine ourselves to spin 1/2 particles. So each of the particles in our two-particle system is a spin 1/2 particle, which means if you ever measure its spin, you will either get plus h bar over 2 or minus h bar over 2. And lastly, we are actually going to be operating under the assumption that these two particles are non-interacting. They don't interact with each other. They both are present, but they don't affect each other. This seems like a little bit silly because what's the point of talking about a system of two particles if these two particles don't affect each other? And it's twofold. One is that there are still interesting properties about the system, even in this very simplistic model. The second is that accounting for interactions like the electric forces between two charges like electrons makes things substantially more challenging, and it's not a great place to start learning things. So we're going to stick with these three basic rules. Again, we're only talking about the spin of spin 1/2 particles, and we are ignoring any kind of interaction between the particles. So they're not pushing or pulling on each other or anything like that. These three rules are basically assumptions about the systems that we're studying, but there's actually one final rule I want to append to this. Mostly about how we're actually going to mathematically write everything down, and that is that we're going to stick to the z basis. We are going to express all of our spins in the z basis. I can still express a spin in the x basis. I'm just going to express it as a superposition of states rather than as x plus or x minus. I'm never going to write x plus or x minus. Everything is always going to be in terms of z plus and z minus. And the reason why that's helpful is because we're going to be writing down lots of z pluses and z minuses. And this way, by decreeing that we are only operating in the z basis, I can drop the z's and I can write everything as plus and minus. Another common notation and terminology that you might hear instead of plus and minus is up and down. So we can also refer to the z plus state, which we are now simplifying to just plus, as up, which we often represent as an up arrow. Likewise, the z minus state, which we're simplifying to be just minus, is often represented as a spin down state, which we can represent as a down arrow. I'm going to stick with the pluses and minuses just because it's more consistent with the notation we've already been using, as well as the fact that I actually find it easier to write plus and minus than up and down arrows, but it doesn't really matter either way. If you go and look for additional resources on this topic, you're very likely to come across up and down, so I want to make sure that you are at least aware that this exists. I might also slip and use the terminology, or sometimes I might even intentionally use the terminology up and down as well. So you should be aware that plus is up and minus is down, and unless specified other words, we're always talking about up and down, plus and minus in the z basis. So for example, the x plus state from before would be written as 1 over the square root of 2 times plus plus minus, or 1 over the square root of 2 times up plus down. So now let's actually talk about a system of two particles. So let's label our two particles 1 and 2. And each particle, being a spin 1/2 particle, can exist in a superposition of the z plus and z minus state, or in the plus and minus state, or in the up and down state. So we can write down a state vector for each particle, and all we have to do is make sure that the probability amplitudes, satisfy the normalization condition, that the magnitude of our state is equal to 1, so the total probability adds up to 1. But the question is, how do we actually combine these two things together? Instead of saying, okay, well, the wave function of one particle is this, and the wave function of the other particle is this, how do I actually combine that into kind of one model? Because I want to talk about the system as a whole, not just particle 1 and separately particle 2. I want to talk about the system of the two particles combined. The first thing to note is that the plus over here for psi 1 and the plus over here for psi 2 are not the same thing. The plus in the first equation, in the blue one, specifically refers to the state of particle 1 having positive spin in the z direction, whereas the plus in the second equation, in the red one, specifically refers to the state of particle 2 having spin up in the z direction. So there is actually, even though they're written exactly the same way, and mathematically we write them down the same way, they mean different things because they belong to different particles. So one way to represent this is to give them subscripts. So I can write subscripts of 1 next to the ones in psi 1 and subscripts of 2 in the wave function for psi 2, just to make it clear that even though we're writing these down the same way, they have very different physical meanings, again, because they belong to different particles. So if I want to write down an overall state vector or wave function for my combined system, it actually is going to have to be a bigger vector than either psi 1 or psi 2, because plus and minus are a basis, the z basis, but for particle 1. The plus and minus in the second expression are another basis, also in the z direction, but for a separate particle. And again, because the pluses are different because they refer to different particles, we actually have 4 basis vectors of our combined system, because we have to account for the various combinations of 1 plus, 1 minus, and 2 plus, and 2 minus, right? Because particle 1 could be plus, and particle 2 could also be plus, or 1 could be plus, and 1 could be minus, and so on. So in order to do this, we have to take these two smaller vectors and kind of mash them together to make a bigger vector. Luckily, there is a mathematical operation that allows us to do just this, and it's called an outer product. Now, if our two wave functions, psi 1 and psi 2, are independent of each other, then I can create their combined wave function by simply taking the outer product of the two. We're not going to talk about the actual matrix math behind this. We're going to stick with Dirac notation, which actually keeps the outer product ends up being very, very simple if you stick with the abstract Dirac notation and you don't really worry about how to write it down as a matrix. We might talk about the matrix stuff later, but for now we're going to stick with just Dirac notation. So what is the outer product? How do I actually write it down? Well, the outer product between two vectors, in this case psi 1 and psi 2, is written, and I'm specifically using the kets of psi 1 and psi 2, is written as a circle with a cross through it. So the outer product of psi 1 with psi 2 is psi 1 with this outer product symbol, and then psi 2. Now, because we actually are going to be writing these outer products a lot, it's conventional to drop the symbol entirely, and so the outer product ends up being represented by simply two ket vectors next to each other. I can do the exact same thing for the corresponding bra vectors. The outer product of the two bra vectors of psi 1 and psi 2 is written the same way, either explicitly with the symbol or by simply having the two bra vectors next to each other. Now, our particles don't affect each other. the particle 1 we established is in some particular state, and particle 2 is in some other state. So if I were to, for example, if I want to normalize the state, I want to make sure that my combined state is normalized. That means I want to make sure that its inner product with itself is equal to 1. So how would I take the inner product of a state like this? Well, again, psi1 and psi2 are independent of each other. So my ket vector of psi1 has got nothing to do with my bra vector of psi2. The psi1 is expressed in the basis vectors 1 plus and 1 minus, whereas psi2 is expressed in terms of 2 plus and 2 minus. So psi1 and psi2 basically don't see each other. So if I want to write down the inner product of our state psi1 and psi2 with itself, our combined state, it ends up simply being the inner product of psi1 with itself times the inner product of psi2 with itself. And again, this is because psi1 and psi2 are expressed in terms of different vector spaces entirely. So psi1 doesn't notice anything about psi2, or it doesn't do anything with this psi2 either. Likewise, the bra vector of psi2 here doesn't really interact with the ket vector of psi1 over here. So only the first half of the bra vector interacts with the first half, or inner products with the first half of the ket vector, and likewise only the second half of the bra vector interacts in the inner product with the second half of the ket vector. So calculating these inner products is actually pretty straightforward because we're just calculating two inner products, one for each particle, and then multiplying them together. Now, one neat consequence of this is that if psi1 and psi2 are both normalized, then their combined state when made through this inner product is also normalized, because if the inner product of psi1 with itself and the inner product of psi2 with itself are both equal to 1, then their product is also equal to 1, and so we automatically have a normalized combined state. So let's do a nice example. Let's have psi1 and psi2 basically be the same, and in this case, let's make it the x plus state. So we have 1 over square root of 2 times plus minus for both psi1 and psi2. Their combined state is then the outer product of psi1 with psi2, which we can write down like this. The outer product satisfies the common rules of multiplication, so distributive property and so on. Likewise, the square roots of 2 are just can all be factored right out because they're just numbers, and so we end up with 4 terms in the end because we have 4 different combinations of 1 plus, 1 minus, 2 plus, and 2 minus. So how do we read this? Well, each of these terms has a probability amplitude of 1/2, right? They all have that in common. Now, if the probability amplitude is 1/2, then the probability of each one of those things being what we measure is 1/4, because it's the magnitude of the probability amplitude squared. So what this means is that there is a 1/4 probability, if we measure the spin of both particles in the z direction, of finding that they are both plus h bar over 2. There is also a 1/4 chance that the first one is plus and the second one is minus. There's a 1/4 chance that the first one is minus and the second one is plus. And there is a 1/4 chance that both of them are minus h bar over 2. This is a lot of writing, though. It's annoying to have to do this much writing. So we often simplify it by taking away the subscripts and combining the kets together so that we have a single ket that simply has a combination that has 2 entries, right? One for particle 1 and one for particle 2, where it's always understood that the first entry is particle 1 and the second entry is particle 2. So now that we have our state, 1/2 plus 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 minus plus minus plus plus minus minus, what can we do with this? So one question I could ask is, what is the probability of finding particle 1 in the state plus? Now, I don't care what is true about particle 2. It could be plus or minus. And so the way that I do this is just with inner products again. However, I have to consider 2 possibilities. One is that particle 1 is plus and particle 2 is also plus. And the other possibility is that particle 1 is plus and particle 2 is minus. So I have to find what is the probability of this outcome and what is the probability of this outcome, and then add those two together. And that gives me the total probability of all the different ways that my first particle can have plus h bar over 2 spin. The easy way to do this is literally to just read it off. Each one of these parts of our combined wave function has a probability amplitude of 1/2, which means there's a corresponding probability of 1/4. And so 1/4 plus 1/4 gives us 1/2. And so there's a total probability of 1/2 that our system, that our particle 1 has spin plus h bar over 2, which we also could have figured out just by looking at our original state of particle 1, right? That's manifestly true from our definition of our original state. So we haven't really learned anything brand new here. It's just another way of calculating the same thing, this time starting from the combined wave function of a system of two particles, rather than starting with just information about the one particle. But if I want to do it mathematically rigorously, then I make use of inner products just like before. It's a little bit different because we have to worry about the two particles instead, but it's more or less the same as before. And you might ask, why would I ever do that? What we just did was really super simple. I don't want to worry about that. But I could ask different questions too. I could ask, what is the probability, for example, that particle 1 would be found in the state x plus? Well, that would be asking a slightly different question. That would be asking, what is the probability that my outcome state for particle 1 is 1 over square root of 2 times plus plus minus? And I can't just read that off the initial state anymore. The first example we did was nice and simple because all I cared about was, is it going to be plus? And there are two parts of our wave function where it is plus. But now I'm asking about the likelihood of finding basically a superposition of the way we've expressed our wave function in terms of the z basis. And so I can't just read an amplitude off anymore. I'm going to have to actually calculate it. So how would I go about doing that? Well, first, I'm going to do this for the simpler example that we already did. What we do is we identify, again, there are two combinations that would have this particular outcome. One is if the system is in the state plus plus, that's consistent with particle 1 being in the state plus. So I want to find the probability of that. And so that is the square of the magnitude of the inner product of the state plus plus with our state psi. I have to add to that the probability that the outcome of our state would be plus minus, because again, that is also consistent with particle 1 having plus spin. And so that's the magnitude squared of the inner product of the state plus minus with the state psi. We can write out this first inner product, and we end up with 4 inner products. But remember that each one of these is really just the product of the inner product of each particle state with itself. And so, for example, this very first term is the inner product of particle 1 being plus with particle 1 being plus, times the inner product of particle 2 being plus with particle 2 being plus, and so on for each of these. And so you'll find that unless the states are exactly the same, the result is going to be 0. Because, for example, here, the inner product of particle 1 will give us 1, because plus with plus gives us 1. But particle 2, the inner product of plus with minus is 0. And so I'm going to multiply 1 from particle 1 times 0. In this third term, it's the inner product of particle 1's piece that's going to give us 0. And in this fourth term, they're both going to give us 0. And so this whole thing simplifies to just this. And this is the inner product of two identical states with each other, which gives us 1. And so this term is going to give us 1/2 magnitude squared for a total of 1/4. Likewise, in the second probability calculation we need to do, the only term that's not going to go to 0 is this part. Because the inner product of this with this will give us 0 because particle 2, the states are perpendicular. And so that's going to multiply everything by 0, so that's going to go away. In this second term, particle 1 and particle 2 match up. Both of these inner products will give us 1. And then in the third and fourth term, in the first case, particle 1 is the one that's going to give us 0. And in the fourth case, particle 1 is also going to be the one responsible for giving a 0, because particle 1 being in the state minus is perpendicular to particle 1 being in the state plus, and so it's going to give us 0. And once again, that's going to give us simply the 1/2 from here times the inner product of this bra with this ket, and then we take the magnitude of that squared, which gives us, once again, 1/4. And so we've calculated a total probability of 1/4 plus 1/4 equals 1/2. If I want to calculate a little bit more complicated probability, for example, if I go back to the x plus example, I want to know what is the probability that my particle 1 will be found to have positive h bar over 2 spin in the x direction. Well, that means this time the outcome I'm looking for is that particle 1 is in the state 1 over square root of 2 times plus plus minus. And again, I don't care about I don't care about particle 2. It can be plus or it can be minus. So the possible outcomes that are consistent with a plus h bar over 2 Sx measurement of particle 1 are if particle 1 is in the x plus state and particle 2 is in the z plus state, and if particle 1 is in the x plus state and particle 2 is in the z minus state. And so I can write that down as a sum of two probabilities again. And it's a little bit messier this time because the x plus state is a little bit more complicated than the simple z plus state from our previous example, but it really does work the same way. To go about actually calculating this, what we would do is we would replace x plus with its equivalent form in terms of the z basis for particle 1. And so now I have the inner product between 1 over the square root of 2 times 1 plus plus 1 minus times 2 plus with psi for the first term, magnitude squared, and same for the second one. There are a number of ways you can go about actually finishing this up from here. I personally like to kind of recombine these into our nice sort of combined state notation. So in this first probability term, we end up with the inner product of 1 over square root of 2 plus plus with psi, plus 1 over the square root of 2 times the inner product of minus plus with psi. And then we take the magnitude squared. And we do the same thing for the second probability term. I'm not going to finish this up for you, but hopefully you can see how you would follow through with this. Now, one thing you might be asking is, why? Why would I do this to myself? All of the work that we just did, and it was, it's not that simple. We could have done way easier just by starting with the original information about the two states that we started out with. So what is the point of all this crap? It seems like it just makes everything harder and doesn't really tell us anything new, or at least doesn't tell us very much new. Well, it tells us a little bit new because it's easier to ask, for example, what is the probability that both of my particles have plus h bar over 2 spin? That both of them are spin up. Well, if I look back at my original states, I know that there is a 1/2 chance that this one is, there's a 1/2 chance that this one is going to be spin up, and a 1/2 chance that this one is going to be spin up. And I said when I first wrote these down that these states are independent of each other, which means 1/2 times 1/2 will give us a total of 1/4. So I can figure it out from these, but I have to do a little bit of extra steps. But over here, it's very clear. There's a 1/2 probability amplitude of both being spin up. I can literally just read it right off the state. Now, this is a particularly simple combination of two states, right? If the amplitudes in these two original particle states were a little bit messier, it's a little bit more annoying even than that. So there's a little bit of an advantage there when in terms of if I care about the probability of the combination of specific outcomes of the two particles, it's really easy to read the result right off of here. I just say, okay, well, I'm looking for this combination or that combination, and then I'm basically done. Although, again, as we did see, if I want to figure out some combination in another basis, it still is a little bit more work. But that would also be a fair amount more work in this example, just doing it the old-fashioned way of finding each one individually first. But here's the real reason why we care about this. we created this combined state by taking two independent states, psi 1 and psi 2. They have nothing to do with each other. Particle 1 and particle 2 don't affect each other. And they weren't related to each other in the first place. But in nature, there are a lot of times where you have multiple particles that, even if though they might not interact with each other very much or at all, their states are not independent of each other. The simplest example of this is the decay of a particle. So for example, consider a electrically neutral pi meson. Pi mesons are unstable. You may recall we spoke about these a little bit back when we were talking about relativity. And they tend to decay into other particles. They can decay into pairs of photons. They can also decay into an electron and positron pair. And electrons and positrons are both spin 1/2 particles. And the pi meson itself has no spin. Its overall spin is 0. And so when a pi meson decays into an electron and a positron, there also must be no overall angular momentum, because angular momentum is conserved. And so if the electron is spin up in a particular axis, then the positron has to be spin down and vice versa. And so this is an example of two states that aren't independent of each other. The state of one is dependent on the state of the other. To write down the combined wave function of this system, now there are constraints. There are, in general, for a spin 1/2 system like this, for two particles, there are 4 possibilities. Either they are both plus, or they're both minus, or the first one is plus and the second one is minus, or the first one is minus and the second one is plus. And each one of those, there can be any combination of those with varying probability amplitudes. In the previous example, we saw one where all of those amplitudes were the same. Here we have an example where 2 of those amplitudes are 0, and the only 2 left over are the ones where the 2 particles have opposite spins. In this decay process, there's no preference as to which particle is spin up and which particle is spin down along any particular direction, and so C and D should be equal to each other. And because there are 2 components, 2 pieces of this wave function to make sure it's normalized, you can check this for yourself. C and D should both be 1 over the square root of 2, which we've seen many times already. Now, in this example, technically speaking, this is not actually a plus. This actually has to be a minus for angular momentum to be conserved. That's going into something that I really don't want to get into right now. We will talk about it a little bit later on. But it's a little bit matter of a phase difference. The magnitude of each amplitude is still 1 over square root of 2. Again, just to satisfy the angular momentum considerations. This needs to be minus for reasons that are not obvious. But just trust me for now. But the point that I really want to emphasize is that it is not possible to represent this state as an outer product of a wave function for particle 1 with a wave function for particle 2. It is not possible to separate these two. They are mixed. They're entangled. It is impossible to describe the state of the electron without simultaneously describing the state of the positron and vice versa. Again, I can't write this as one of these outer products of a state for particle 1 with a state for particle 2. They are inseparable. And so when you have a system of multiple particles and the nature of those particles or the state of those particles is dependent or are dependent on each other, maybe because of the way they were produced or maybe because of something you've done to them. But in these circumstances, there is no way to describe the system as 2 separate particles. We can only describe the system as a combination of 2 particles because there's more information than what would be present in a wave function for any particular particle. I really want to emphasize this. In this example, a pion decaying into an electron and a positron, there is no way to describe the state of one of these particles without the other. If I'm holding on to an electron from one of these decay processes, it is impossible to determine or to express this particle state without also expressing the state of the other particle that was produced in this process. It's a very strange thing, and we'll talk about this in much more depth. But this is really why we care about this whole process of writing down combined states, because it turns out that there are systems of particles that cannot be described as individual particles. It's simply not possible to do. And instead, the only way to describe the system fully is to talk about the combination of the particles themselves. This is basically getting to this idea of quantum entanglement, which is a very fundamental feature of quantum mechanics. It's something that has led to endless decades of debate over the meaning and the nature of quantum mechanics and how we should actually interpret what is going on in these systems. We will talk more about entanglement in much more depth going forwards, but for now, let's just practice with the tools and the mechanisms that we've established here.